Well, the last part of our introduction to vectors is dealing with a vector and its direction angle. Now, we've not been specific about directions except just physically seeing the direction of a vector based on its initial point and its terminal point. But we can also describe the direction of an angle by the direction of a vector, pardon me, by the angle that it makes with the positive x-axis. So imagine here that our angle v is the vector that starts here at the origin and goes all the way out to this position. Ignore the u in there for now. So think of the vector v as the vector that goes all the way out here. Well, the angle it makes with the positive x-axis, and we're going to measure in a positive way, then this angle right here, which is named alpha, is called the direction angle. And so we can, if we have a vector that has a direction angle of 60 degrees, we know that vector is going to go off in this direction, don't we? Or if that vector has an angle of let's say 120 degrees, then we know that that's going to go off about like this. See, something like that. So anyway, the angle that it makes with the positive x-axis is called the direction angle. And we can determine the component form of a vector based on its direction, angle, and its magnitude. And this is the little diagram that helps us understand that. So the idea behind this diagram, again, is let's think of the vector as we can't see the bottom part of it. The vector starts at the origin and goes all the way out here. That's the vector v. Now, of course, there is a unit vector that is in the same direction as that vector v, and that's named u, and it's a unit vector. So we're kind of thinking about, okay, this distance along here for u is 1. It's a unit vector. Well, imagine that the point that's at this unit vector, that's on a unit circle, isn't it? Because that could be thought of as the radius of a unit circle. So that's the idea of this arc being shown, okay? So this vector that we have in this position, this unit vector, because its endpoint is on the unit circle, and so the coordinates of that point that are on the unit circle, the coordinates of that endpoint, are based on this angle alpha. And so the first coordinate is the cosine of alpha, and the second coordinate is the sine of alpha, since we're on the unit circle. Well, so we know the vector u we know the vector u based on that information in component form, or in terms of the basis vectors, or the standard unit vectors. So this vector u has the first component of cosine of alpha and second of sine of alpha. And likewise, we can write it in terms of I and j. Well, this vector u is the same direction as v. How would we normally determine, remember way back when, let's see if I have way back when, in fact, let's even look further. Remember the way we calculate u. Let's look up here. The way we calculate a unit vector in the same direction as v is we take v and divide by the magnitude of v. Well, look at this little equation and multiply both sides by the magnitude of v. So we end up with v is equal to the magnitude of v times u, okay? So we already know the unit vector u. And so to come up with the vector v that we're trying to get in component form, we take the unit vector u that's in the same direction as v, and we multiply it by the magnitude of v. That only makes sense. We've got a vector that's in the same direction as v, and if we multiply it by the magnitude of v, now we make it the same length as v, and it's going to be in the same direction, so it's the same as v. So the little here then we see we're going to take v, we're going to define v as the magnitude of v times the unit vector u. Well, here's the unit vector u, okay? And so we can think of this vector v in this form in terms of the component form, or we can think of it in terms of the form with i's and j's, okay? Either way is appropriate and useful for us. So that becomes very useful, in fact, in a lot of our problems. Remember, if we know the angle the vector makes with the positive x-axis, and we know the magnitude of the vector, then this is the way we define the vector, or here's how we calculate the components of the vector v. Well, let's look at the next page, and we'll go through actually a problem here. So we're supposed to find the component form of the vector, and sometimes, of course, that's called the position form. The component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle 30 degrees below the horizon. Now, I've chosen to draw the diagram in this fashion, okay? I guess I'm thinking of the plane flying, if you will, to the west, maybe. But this is just the diagram that I decided to use, and we could have done it a little differently, I suppose. So the vector is, the airplane is descending at a speed of 100 miles per hour. So what I've got then is the length of this vector I'm using as the magnitude, and that's 100. Okay, the magnitude of the vector is 100. That's what the speed is telling us. Now it's traveling at 30 degrees below, if you will, the horizon. It's descending at an angle of 30 degrees below the horizon. So I'm thinking of the x-axis as the horizontal as the horizon. And so 30 degrees below would be here. So the angle altogether, though, the angle is making with the positive x-axis, this 180 plus 30 more is 210 degrees. And so my direction angle that I called alpha on the previous page is 210 degrees, and the magnitude of this vector is 100 because of the speed information. Well, now here I'm calling the direction angle by the name theta rather than alpha, but obviously it's equivalent. And I got a little bit lazy when I was writing in the magnitude. I just used one absolute value here. But the vector v that we're referring to here then is the magnitude of v times the components of cosine theta and sine theta, which are the direction angles. Well, in this case, the magnitude of v is 100, and this direction angle is 210 degrees. So I've calculated the cosine of 210 degrees and got negative square root of 3 over 2. Calculated the sine of 210 degrees and got a negative 1/2. Of course, my magnitude is 100. And now I've just got a scalar multiplication. So I multiply 100 by each of these components. And of course, when I multiply by 100 here, I'll have a 100 over 2 will reduce to 50. So I've got negative 50 root 3. And here, of course, 100 times a negative 1/2. Is simply negative 50. Now, this is the way I prefer to do that. But remember, we've also talked about writing v in terms of i's and j's. And so if I would have done this in terms of i's and j's over here, then my magnitude of v is still 100, and I'd have cosine of alpha, that I've called it here, times the standard vector I plus sine of alpha times the standard vector j. And so still a cosine of 210 degrees is negative square root of 3 over 2. So I have that times I, and I have here a negative 1/2 times j. So rather than saying plus a negative 1/2 times j, I've written it as minus 1/2 times j. And so then when I multiply that linear combination by 100, then we just get simply v is the vector negative 50 square roots of 3 times I minus 50j. And we could have converted that here with i's and j's that we've talked about in previous little vignettes, lecture vignettes. Now, it might be of interest. That's not what we're asked to do here. We're just asked to find the component form of the vector that represents the velocity. Okay, and that's what this is, the velocity of a plane descending at 30 degrees below the horizon at a velocity of 100 miles per hour. This is the vector that represents that. But we could here, in fact, verify that that vector has a magnitude of 100. So here's the vector. If we're calculating its magnitude, it's the square root of the sum of the squares of the components. And when we square negative 50 times the square root of 3, well, when we square negative 50, of course, we get 2,500. And when we square the square root of 3, we get 3, so we'll have 2,500 times 3, or 7,500. And likewise here, when we square negative 50, we get 2,500. And so that's the square root of 10,000, and the square root of 10,000 is in fact 100. So we have verified that, although that wasn't part of the original problem. Well, I hope this helps you get what you need done for this homework assignment, and good luck to you.